All right, so I'm going to talk about systematic error handling in C++. Systematic meaning we're taking an organized approach to error handling as opposed to sort of just incidentally, I'm going to use exceptions here, I'm going to use an error code here, I'm going to handle exceptions in various ad hoc ways. So let's look at some systematic ways to handle errors. After an introduction, I'm going to discuss two artifacts intended for error handling. One is expected, and the other is scope guard 11. Scope guard, you may remember, is an old article that Petru, Morginan, and I wrote back in 2001 or so. It was, incidentally, it was the most successful piece of software I wrote, which is kind of a bummer because I wrote it with a friend. I had to share that, the fame, if you wish. So scope guard was quite a successful idiom, and it turns out that in C++11 it can be made much better. So a lot of possible disadvantages of scope guard are gone in C++11, making the resulting code much more efficient and just as good from an error handling perspective. So, well, let's start with the definition. We want to be systematic, right? So error handling, I would say it's the collection of means and techniques dedicated to handling possible but unexpected and useless inputs. So why am I focusing on inputs? Because that sounds like, oh, so if I take care of what I'm doing with that file, that should be enough. Well, as it so happens, of course, the world is much more complicated, and the reality is a lot more complex than we might think. So error handling is about bad input, not about bad states. It's not about bugs. It's about data errors, not about errors that programs have made. And to substantiate that, let me actually contrast with general reliability, which is a different topic, which incidentally includes some of the error handling topics. So let's see. So we have error handling, which assumes working core, which means the basic assumptions of the type system are holding. If you put an int, you're going to find an int. If you put 42, you're going to retrieve 42 later, and so on, right? So the basic guarantees of the type system holds. The RAM works. See what I'm saying? The RAM works, right? Correct program, meaning, well, I have a program that is supposedly correct, free of bugs. We're not focusing on program bugs. But the program may have incorrect inputs. And that may mean like network inputs, might mean keyboard, whatever, file I/O, and so on. So the environment of the program is feeding erratic, if you wish, input into the program. Let's contrast that with general reliability, which is a very interesting topic, which means memory is not working. So you put data in it, you retrieve something else. Cosmic rays, a bullet through the motherboard could cause that. Actually, there's a famous demo with a guy who put a bullet through a motherboard, and the system, which will consist of like two computers, continued to work at half speed, uninterrupted. So it assumes the memory is not working anymore. It assumes the program may be incorrect. It assumes the inputs may be incorrect. So that's the only identical part. So general reliability, just to open a quick parenthesis here, has to do with things like, running two algorithms on the same input, vote, 2 or more, right? So you get a vote of 3 or more. You run on 2 different systems, compare and contrast the results, shut down, emergency, switch to manual control, you name it, depending on the system, and so on. So, the Mars probe has a lot to do with this kind of stuff, right? We're going to handle this kind of stuff, okay? So getting to error handling scenarios, as I said, we may have user input issues, file I/O, networking, environmental, device malfunctions. And by this, careful here, when I say device, that's not part of the core. They're connected to the system and they work badly. But the RAM still holds. I'm insisting on this notion of the RAM working because the RAM is the home of any guarantee you may hope about a program, right? So RAM is different. like file bytes on disk and whatnot, that's a different matter, but the RAM is important. All right. Reliability scenarios are different. So let's contrast, you see, so we have like error handling scenarios, and we have reliability scenarios, which are very different. Program bugs, unexpected state in the program, corrupted I/O, core memory failure, and more. So my hypothesis for the rest of this talk is the following. Very simple. Bad error handling engenders errors in the program. So it evidentiates errors that programs might have made. Then insufficient testing makes it improbable that, makes it unlikely that you test for all error scenarios, because errors are rare, and if you don't test specifically, like proactively for these rare cases, they're not going to occur very often. So they're going to occur, of course, in front of your most important client and so on. So insufficient testing makes it improbable that error scenarios, all error scenarios are going to be covered. And what's going to close the cycle here is that legit errors, input errors, are going to lead to corrupt programs. And of course, if you were to choose, where would you focus your efforts on? Let's see if I chose the same. I did. All right, so we want to stop the issue at its core, because it's the bad error handling that is going to create the metastable states in our program. Is going to reveal states that the program wasn't prepared to handle, like you have a negative date and you have a 0 day and things like this, which are like odd, and the program is not prepared to handle. So it doesn't that state doesn't make sense. It came from an invalid input early on, and it reveals an insufficiency in the program. So the best way is to stop the issue at its core. So, as an example, I lived for 4 years in an area with very unreliable internet connectivity. I've used Thunderbird for email, like just like many of you, on an everyday basis. And actually, in Thunderbird, it's a very good analysis to see just how bad error handling can be done. Because I wasn't kidding. I'll let you know when I'm kidding. I'm not kidding. So actually, in Thunderbird, if you play with Thunderbird in the way, like, for example, you randomly connect and disconnect your networking, you're going to see a lot of very Byzantine failure scenarios. Like Thunderbird may get into infinite loops. It's impossible to close it because it says retry, I couldn't do this, retry, and if you cancel, you lose everything, and if you retry, it's not going to work. It has, everything is modal, so you can't, it doesn't actually let you know amodally that something went wrong. It requires immediate attention, and then of course there's recurrent errors and stuff like that. Has a lot of race conditions. If it just so happens you disconnect between the time a message is sent and the time it's supposed to be saved into your sent mail folder, which is also remote, you don't want that to happen. Has metastable states and broken core invariants. What I mean by broken core invariant, like when Thunderbird started, it was very nice because it was a small, reliable program. And with time, more features crept in. And unfortunately, they eroded like very core functionality. You can actually get screenshots in Thunderbird when the message highlighted on the left pane, the message highlighted in, the header highlighted is not identical to what you see. So actually see a message that's not the same as the message indicated, which can lead to pretty dangerous, communication errors between people. So, leaving that all aside, let's discuss some implementation. So let me start this discussion on expected with, there's no code available for expected. There is code available for scope guard in Facebook's Folly library, which is our public C++ library. It's on GitHub. Expected is new enough to not have yet an implementation in that code base. But I'm going to give enough implementation directions for you all. So the motivation of expected, I'm going to tell you what it is after giving the motivation. So exceptions are, let's say, good. It's still in the air whether it's best to use exceptions or not, right? It's, it's a hot topic still. in which I gotta say, I'm taking no sides. I think sometimes they're good, sometimes not so good. I don't think we have a very good handle on how to use them well. The one main problem is that the code is very slow on the exception path. So we've had that Facebook, we've had this, this issue. We use exceptions to handle errors in parsing some data. And it turns out that sometimes you want to parse in an integer if it's an integer, otherwise you want to skip it and parse some text. It's just a choice. It turns out that if you try catch the error, and on the catch you kind of do the alternate computation, what happens is the code is going to be 50 times slower. And if you multiply that with a long file that you need to parse and has many such cases, it turns out it's unusable. It's, you simply can't deal with exceptions that way. So in that case, we had to switch to error codes and such. One main issue with exceptions that is becoming obvious with the many-core revolution is that exceptional code is hopelessly serial. So exceptions, there's only one in flight. I mean, how quaint is that, right? There can be only one exception at any moment in flight. If you want more exceptions in flight, you gotta have more threads. But then there's no obvious way to collect them together. So there's additions to standard for handling such cases. But in any given thread, there's only one exception that's there, right? It's kind of weird. It requires immediate and exclusive attention. It comes to the fore, it's there, you must handle it right now. There's no sort of, well, let me handle it later because right now I'm dealing with some more important problems. And they require dedicated control flow, as we know very well. And one sort of a high-level issue is that exceptions are associated with root reasons, not ultimate goals. Like, exception, error, I can't open file, I can't read from file. You see these messages, and what was I doing here? It's not like, oh, I was saving the wait file, I was reading opening the database or whatnot. So very often it just so happens, and I'm sure all of us have seen such scenarios in which, well, nothing new here, error codes, the error messages are just, weird. So it's not only the compiler writers who have bad error codes or error messages, right? It's us too. So let's do this. Well, a common complaint about using error codes, on the other hand, is, well, error codes are integers. I mean, with exceptions, I can actually transport an arbitrary amount of information about what went wrong, right? So exceptions are great because they're rich. So I can say, well, this didn't work out because this happened, couldn't open the database. While I was opening the database, the password was not very good. And you can actually transport any amount and any kind of information with an exception. With an error code, it's kind of, gotta predefine them. I mean, we all know how it's like to have int as the only information about an error. So the obvious solution, the key insight here is let's make exceptions be the error codes. So all of a sudden we have error codes that are infinitely informative, just like exceptions, but they don't have all the drawbacks that we just discussed. All right, what would that look like? What would you think? Yes. You just derive from studio exception. Yeah, so that as far as the error defining the error codes goes, yes, you would derive from the exception hierarchy. And to transport that kind of information, let's do this. Expected of t is either a t or the exception that prevented its creation. So I have an expected, I'm expecting that it's a t because that's the more frequent case, right? But if it's not, the same value encapsulates an exception that contains whatever happened that prevented that t from being created. This is, I mean, is this there? All right, let's see how we can make it happen. But before that, let me show you a couple of examples of how we can do it. Let's say parse int, and we have a string, and we parse the int, and like the famous A to I mistake, like they return 0. Let's return a number that's impossible to occur in normal input, and that shall be 0. All right? Actually, it's kind of funny because like the work, so you parse, you return 0, and if you return 0, you gotta go back to the string and see, does it look like a 0? Because if it does, it's legit, right? Otherwise, it's not good, and you need to. And that kind of code is probably the same complexity as actually writing the blessed function yourself, right? So not good. Agreed? I hope we all agree that this is not good. This is almost going there, but so this might actually throw two kinds of exceptions in this hypothetical design. So we have invalid input if you're passing ABC for parsing as an integer. That's invalid input. More interesting, it could overflow. You could pass like, as for a 32-bit integer, you may pass a string of like 30 digits. It's going to overflow, right? You want to detect that as well. Right? Many codes don't. So rich information, that's very nice. The problem is it's going to be thrown. If you call this in a huge loop, and it may fail often, then you're going to have a serious performance issue. So instead of all of this, let's go for that. How about that? So we have parseInt, and it returns, it takes a string and returns an expected integer. So it may be an integer, but it may be an exception underneath, encapsulated within the return value. So this is kind of nice. And then I can actually look at this thing and say, was it an error? What error was it? And stuff like that. So in the typical error code programming manner. Or I could just fetch the integer blindly, in which case attempting to fetch the integer to sort of, decoherence, exercise decoherence on that expected is going to throw an exception. So I'm back to exception style error handling, right? Very nice. There's some related work on this. So, this might actually sound familiar to many of you because, everybody knows Haskell, right? Or wishes they know. Right? It's like the language that everybody wishes they know, right? So in Haskell, there's a nice abstraction of maybe T, T being pretty much any type. So if you say maybe T, it's either T or nothing. And it's the nothing I take issue with because you don't want nothing. You want, you want some information there, which is why isn't the T there, right? Very nice. Scala, option of T. They copied what Haskell did. It's the same, let's say, mistake, same unhappiness, same level of unhappiness I'm having towards that abstraction. C# has nullable, or T, I think it has a syntactic shortcut, T question mark, right? So nullable means, it could be an integer or nothing again. So we have either a type or nothing at all. And I want to make progress from there, right? I want to say I have a type or why there's no type there. Well, there's no value there for that type, right? Boost has an optional T. And all are the same kin, right? So it's either a value or nothing. So all of these abstractions define, the classic primitives that you'd expect to store, test, extract, and they're not packed with any information about error. There's more related work, actually, which is where things start to get a bit interesting. Promise and future. Either a value of type T or an exception, which, wow, almost goes home. It's almost there. Except the primitives are really focused on inter-thread and asynchronous communication. You can poll, you can look, is it there yet, and stuff like that. So there's mutex is inside these types and such. So this is very close. Actually, both, this is close, but neither hits home. We want eager synchronous values, simple, without much overhead. All right, so before we get into, let's see if the next slide, yeah, we start with, so before we get into the implementation, let's look at what features we're looking at in expected. So, first of all, it associates errors with computational goals. Yes, Scott. Herbie is going to save me.
I wondered the same thing.
And?
So, by the way, I also, like you, have not looked at anybody's slides except this one. And so I have some comments on it later, but it's great stuff, because I wondered this too. And so I actually ran a performance test on one compiler and one implementation of Future, and the performance overhead was about 10x.
10x is not something
No, not using async, just using promise and future directly versus using the expected T Andrei is going to show.
Right. So actually, this particular slide is the outcome of a conversation that Herb and I have had, which I'm going to get back to. But just to summarize, never underestimate Herb's power. All right? So he did the right thing here, indeed. So he called me because he saw my draft slides, and he's like, oh, yeah, this is very exciting. So, how about using promise and future for that kind of thing? And we're looking at the APIs and stuff, and there's got to be some mutexes in there, and it's not what we want there, right? So, getting back to the show, if anyone is still following. So, the nice thing about expected is that you associate errors with computational goals, and that's great. And let me remind you of some other things that associate, for example, like when you have things like atomic, right? You associate the notion of locking with the notion of having a value in there, right? Very successful. Then you have things like synchronized classes, right? Another very nice, like you associate the mutex with the data it is protecting, right? So it's very powerful to be able to group together things that belong together. Sometimes, granted, it may be the case that the error, computation is not obviously associated with the outcome of that computation. But I would argue that very often that's the case. So you actually want the product of some computation, or you want to know what the heck happened. And it's very nice that these are associated together by design as opposed to just by, by the flow of the code. So this is very important. Errors are associated with computation goals. Very nice. Naturally allows multiple exceptions in flight. So you can have like an array of exceptions of vector. I mean, all of a sudden there are regular types that you can use naturally without having to, there are a lot of tricks that you need to do with exceptions. Like, how to retrieve the type of an exception. You say try, throw, and then you catch it and look at it and stuff like that. I mean, isn't it that bizarre? You need to handle it just like any type. You can switch naturally between error handling style and exception throwing style. So if you want to do error handling style, error code style, you say if the expected is actually what I expected, then do this, otherwise do that, so classic style. Or you can just fetch the value underneath, and you're going to have an exception thrown automatically. Teleportation possible. Teleportation, I mean across threads. But you can not only teleport across threads, but you can actually teleport an expected across no-throw subsystem boundaries. And you can teleport across time, save now and throw later, which is a very nice artifact. So what if you parse a whole file that's in 1 gigabyte worth, and you have there are 50 errors in this file, right? So you accumulate an array of these guys, and then later you can actually look at them, throw them, whatever. You can collect and group and combine exceptions, which I think is a woefully underexplored area, because very often what happens is one exception, begets others. So I couldn't read from the file, and then you try to close the file. I couldn't even close the file, and then trying to close the database, and I'm not connected anymore, and and stuff like that. So it's sort of a chain of mishaps that's happening, and actually very often you're interested in knowing exactly about everything. And in C++, with the classic exception flow, you can only have one exception. It's impossible to combine with another exception unless you work very hard. So with expected, you can actually pretty easily play with exceptions like that because you deal with them as usual C++ values. All right, so far so good. Are we convinced that we expect expected to be great, right? Are we there? Okay. Let's implement this thing. And I'm going to implement full-blown C++ 11 style, which is very nice because, for example, I get to have a union of a type with a constructor, which was not possible before. It is possible now. I'm sure they had this application in mind when they allowed that. It's very nice. So we have, basically, we have a variant, boost variant or such, right? It's a variant which may hold one of two types. One is a T, the other is an exception pointer. Exception pointer, hands up if you know about it. Hands up if you know. Okay, great. So I get to introduce to you a very useful abstraction. This is new to the standard, and it actually encapsulates opaquely a pointer to any exception. And it has primitives for duplicating and passing it along and moving and whatnot. Let's say actually get to encapsulate an exception. A lot of hard work is avoided in the client code by using exception pointer. And the way it's implemented internally, I think, is it's a shared pointer to an STD exception. It's a shared pointer of an STD exception. Great. So we have class expect, and we have, in the private area, we have ham or spam, right? And, right? All right. So it depends on how you pronounce it. You can go different ways. And we have an empty constructor that's used internally. Because usually when you want to initialize an expected, you want to make the decision it's ham or spam, right? All right. And now we have a little wall of code. Don't get too excited because it's quite easy actually. So we have the obvious suspects. So you have an expected that takes constant reference to a t, a reference to constant t, and we initialize the ham, and we initialize got ham with true, Gotham if you wish. And then we have the move constructor, all this paraphernalia that is doing the same thing, except it's also moving the thing, so we save a copy if there was one. And then we have the copy constructor, which is a bit interesting. So when you copy, got ham, it's just a Boolean there that's initialized. And here we have, do I have ham, in which case I'm going to new at the edge of the member, I'm going to new a t, copying the ham from here. Otherwise, I'm going to new the exception pointer that's copying the pointer from spam. Interesting. It's interesting in a way that it's code that you need to, the design imposes the code. See what I'm saying? It's not interesting code in the sense that, wow, look at what idea I had here. No, it's interesting like, this is forced code. I have to write it this way because of the design. So interesting artifact. And then I have the move constructor, which is going to do the same with the Boolean, and then I'm going to do pretty much the same pattern, except I'm going to have a move here and a move here. I'm moving the thing, right? Why didn't I use std move here? That's an attention check here. Why didn't I use std move here? Huh? Oh, okay, only one at a time. It's just a Boolean, all right. It's just a poor Boolean. It doesn't matter to move it, right? Again, attention check. That half attentive, that half not so much, all right? I'm looking at you, all right. So very nice. So far, so good. Are we, this is clear? Yes. Tim? Huh? Why is it a placement new? Well, again, it's imposed by the design. The design says I have a Boolean that tells me which of these is valid, which of these branches are valid. And essentially, I need to initialize one of these there, depending on the Boolean, right? So what I do, I need to deposit inside. So this union, once I have a union, the compiler is not going to initialize it with anything interesting. So once it's a union, all bets are off. I need to take care of my own initialization, and that's what I do here. I knew in the place of ham, exactly where I want it, I'm going to create the thing. So don't get confused by the existence of the new here. I'm not allocating anything. It's not an allocation. It's more a hint, not a hint. It's a directive to the runtime system to create an object at that specific address. Yes? I couldn't use an assignment because assignment assumes the previous value was valid. Oh, thanks. That's what you, okay. So you wanted to force me to say this, and now you had it. All right. Thanks. Yeah, that's the clear way to say it. Excellent. So we have, the usual suspects here. And then we have some, again, a forced function which turned out to be fairly interesting, fairly large, swap. Swap is important. It's good to have swap, right? You want to have swap. So, swap is interesting because it's a collision case. because it takes care of, it needs to look at both the state of the left-hand side and the state of the right-hand side to do its deed. And the actions are kind of different in each case. So let's see. Well, if I got ham, if I'm at a t and the other is also a t, I need to swap the t's. And I leave the Booleans alone because they're already good. Make sense? So far, so good? All right, so do you know why this using is here? Somebody who's not Herb or Scott. Yes? Because otherwise you would have a recursive call. Actually, no, it would not, it has two parameters. Actually, it's kind of interesting. So it's two reasons. It's two reasons. So reason number one is if I take out this using, the code will not compile because swap is going to look at this one and it's going to say, you know, bad number of parameters, of arguments. This can't work. So this actually brings swap. But there's another reason for it. Why didn't I just write std swap of ham and RHS.ham? You just asked a question, you're not allowed. Somebody else. Yes? So you can specialize the swap in RHS's namespace, in T's namespace, right? So this is sort of the standard sanction way of swapping things. You got to say using, you know, committed to memory, it's memorization. This, you know, this is how it works. And the way it works is you actually bring std swap into the namespace for lookup availability, but then you just call unqualified swap. And if it happens to be, if there happens to be a swap in T's namespace, it's going to pick up that guy. Otherwise, it's going to pick up std swap. Grace to Koenig hates to call it Koenig lookup, so let's call it argument-dependent lookup. All right. All right, so let's see. So the left-hand side got ham, and the right-hand side didn't. So what we need to do is take the spam out of the right-hand side, put it in my own, then put my t inside the right-hand side, and then put whatever the exception was in the right-hand side here. Right? Ultimately, I'm going to also have to swap the Booleans, and since Boolean is a primitive type, I get to write std : swap, and it's correct. Right? All right. Otherwise, here I allowed myself to be just a bit lazy, because I'm going to recurse. Right? So if I don't have ham, so I'm in an exceptional state, but the other guy got, it's this code with changed names. Right? It's the same script, different, you know, the names are swapped, right? So I'm going to recurse. I'm going to say, well, let me actually swap RHS with myself, and I'm done, right? The runtime cost, there's going to be a couple more tests, right? And in the last case, I only need to swap the exceptions. And again, I need to swap the Booleans, and I'm going to need to swap the spam, the exception pointer, which happens to have a swap member. Make sense? I have 4 cases, 2 Booleans, 4 cases. We simplify in one case, we handle the others as they should, right? All right. Yes? The classic copy constructor, yes. Here? Yes. What happens if that guy throws an exception? I'm glad you asked, because you know, remember what Scott said, the new material and the 4 stages of grief and stuff like that, right? So I'm starting to face like, is this code actually working here? Okay, so let's see what happens. If this guy is going to throw, we're throwing from the copy constructor of expected, which means the expected was never actually created, right? So there's no problem with destroying something that's not there, so the code is, at least on the face of it, correct. One argument that could be made would be, well, maybe I want to actually catch this and put it here. Maybe I want to copy a guy. I would argue that's not a very sensible design, but I think it's definitely a possibility. I think it's a good point. But you know, let's say this code is correct for my intentions, right? So I never get to destroy something that wasn't completely constructed. Yes? A copy constructor? Yes, I could. I mean, in pure theory, I could. The problem is I need flow, because I need to construct different objects depending on a Boolean. So I need flow. Yes, Scott? Thank you. So the question was, well, you know, while of displacement new stuff, when you could actually use colon, and then you get like, you know, you get to invoke the copy constructor automatically, right? Well, the problem is I need flow, because I need to initialize different members depending on a Boolean. So syntactically, I can't do that. Yes? I don't want to copy null over T because the T may be there. It's a union, okay? It's not a struct. So I could actually, I could have an easier life if I didn't use a union here, but actually this can save us quite a bit of space, right? So I'm having this packed design, if you wish, because I know only one is going to be effective, right? So I want to save some space, which leads to some of these contortions. All right, and finally the destructor, again, is sort of interesting syntactical detail here that I wanted to share with you all. Okay, let's see. Well, if I have ham, I need to destroy the ham, right? So I say ham dot, you know, destroy T. Otherwise, I need to destroy the exception pointer. Why this using here? Why did I need a using statement there? Yes? No, it's actually much simpler than that. So you have spam dot, you know, tilde, and then you would need to put std colon colon, right? It turns out that tilde following by symbol colon colon does not parse. And that's how the cookie crumbles. All right, so, you know, so just so you know, if you ever need to destroy a type in another namespace than yours, do this, okay? All right, don't shoot the messenger here. Okay. So we've dealt with, let's say, the usual suspects, which were, you know, I want to construct an exception from a T, I want to copy it around, I want to move, all that good stuff. But at the end of the day, we want to create from an exception. We want to create an expected. That's the bad case. You know, I had the problem here, so let me actually create from an exception. So here's another interesting forced function, which would be, well, you know, I'm returning an expected, and it's a static function that starts from exception, and then it takes an exception value. And here I have an odd test. Could someone tell us why do I need that test? All right, I'll tell you. I have no idea. Okay, I'll tell you why. Here's the thing. Exceptions have ambiguous gender. They're an odd type. Like exceptions as a kind, if you wish, as a class of classes, are bizarre in the sense that they are at the same time value types and polymorphic types. They are value types, so when you want to throw them around, when you throw by value. You say, I'm going to throw a runtime error, I'm going to throw an invalid argument, I'm going to throw my exception or whatever. So you throw as a value. When you catch, you got to catch polymorphically. You catch, you know, never catch by value. You know the Dutch, right? You know the coding standard. You never catch by value because you slice the thing and you get the bad error messages and the wrong types and everything. So you catch by reference. Why do I catch by reference? Because it's polymorphic. Because it has virtual functions. Like what is a virtual function? Has a virtual destructor. All those good things. So you throw by value, it gets transported as a value, and you catch polymorphically. You catch by reference, which is unlike anything else in C++. This is unique. Okay? So this is interesting. It's sort of, it's a blip on the radar, okay? So when we realize this, we also realize that we need to handle exceptions with particular care. like in this example here, I'm taking a const E reference exception, which may lead us to believe that we're dealing with a value because it's an economical pass by value, const reference. Everybody does that, const string, right? So this does not betray the polymorphic nature of the object. Therefore, what I'm going to do, I'm going to insert a runtime test here to make sure that the dynamic type of the exception involved is the same as its static type, to make sure that I don't have an inadvertent copy in there. If I had, at this point, I would have slicing, because I would copy a fragment of an object. Make sense? Questions? All right, so that means it doesn't make much sense. So this is a classic test. You're going to see this test. You should insert this test whenever you deal with exceptions because you must make sure that at all points in your computation, you preserve their being polymorphic. And you're going to see the test in cloning scenarios when you want to clone polymorphic objects and you want to make sure that the clone is of the same type as the original, right? So these are two classic scenarios. The first one was, was figured out years ago. This is rather new. Yes. All right. So there's a bit to explain, and actually, Herb, I'm going to destroy him in the process of doing so. But let's start with again with the usual suspects. So expected means either a T or an exception. Yes? How do I initialize it? Well, I know how to initialize it from a T because I do this. I have this constructor. Now I like move constructor, but this is important. This is the important tidbit of information. I have expected of int. I have expected of int, and I initialize with 42. It's going to work because of this constructor, right? What if I want to define an expected of an exception? Well, I could write a constructor that takes an exception, right? But then, how about this? What if I want to, all right, so what if I have a expected of string, and I want to throw a const char star? Wow, this is interesting because const char star converts implicitly to a string. So if I try to define a constructor that takes a const char star, then that guy is going to actually go to the string or actually be intercepted. And either way, I might get what I wasn't expecting. I either want to initialize with a string. I say expected of a string blah, blah equals hello world, right? And it goes to the exceptional case. Where was the exception? Oh, it was because it's const char star, and that's a better match for the exceptional case. Oh, wow, so this is interesting. So at this point, another sort of weird scenarios. What if I have an expected of float, and I want to throw an int? Oh, wow, so you say expected of float, if you initialize with 0.0, it's going to work. If you initialize it with 0, it's not going to work, because it's going to go to the exceptional case. So we have all of these weird cases in which the exception is close enough to the type that the spam is close enough to the ham that it makes for confusing and ambiguous cases. Because of that, I decided against Herb's advice, which is gonna tomorrow morning he's gonna destroy all of this. He's gonna make it hack all over it. But today I got a microphone, okay? So
I'll destroy it on Wednesday.
All right. So in this case, we have a constructor that's the classic way, which means constructor means ham. And then I can't afford to define another constructor for spam. So what I'm going to do is I'm going to say, well, let me define a static function that returns an expected object, and it takes an exception as an initializer. And that way I can syntactically distinguish the ham case from the spam case. Okay, I see some nods in the audience. Yes? Is it possible to move that check from runtime to compile time, right? This one? Okay, well, it's, the short answer is because what if somebody catches an STD exception? So try catch. And then they call this function with the STD exception. In that case, what we have here is, E is going to be STD exception, but the actual type of the exception may be anything derived from STD exception. In that case, the error was made upstream already, and the call has no chance but to check it dynamically. So there's no possibility there to cheat death a bit. All right. Yes. Oh, yes. Yes. When you create this guy, you must have the, the most derived, the actual type of the, this must have like, value semantics here. And in the back? Wouldn't using explicit on a constructor help here? No, because explicit would be would apply to everything. So it's explicit of the good case and explicit of bad case. In either case, it's same deal. What I'm talking here is not inadvertent calls to this guy, which is what explicit would prevent, but I'm talking about ambiguous calls with different types. So now just to anticipate a bit Herb's side. So Herb got unusually excited about this. So Herb calls me on Sunday. Herb called me 3 times in my life, okay? One of them was last Sunday, a couple of weeks ago. I sent him the draft, and he's like, Andrei, I'm very excited about this. So first of all, can't future and promise do that? And I was like, well, all this mutex stuff, and I'm going to check. He did 10 times difference. I'm good. All right. Second, he's like, oh, so this kind of from exception, this looks really awkward. And he had a great design idea, which I agree with. I think it's a good design, which is going to substantiate tomorrow morning. So stay tuned. So right now we have building from exception with an exception object, and we also have sort of by necessity from exception with it just so happens somebody has an exception PTR, and again, that's good. And here we have all sorts of weird cases. What if I want to build an expected of STD exception? That's a bizarre case, and maybe some people might want to expect an exception. And in case that doesn't work, an exception is going to be thrown. So it's all of these corner cases that make this design sort of difficult to put together. And this is one of the solutions that I came up with to put it together. Another case is like, what if I have an expected of exception PTR? It could be I'm expecting an exception PTR, and if not, I'm going to have either an exception PTR or another, which is, again, it's all about that Boolean there in the got ham. So finally, I have from exception with no arguments. In that case, I'm going to pick the current exception. C++11 added the current exception function, which returns whichever exception was in flight. And if there was no exception in flight, the program is not going to terminate. Fortune is going to return like the null pointer to exception and stuff like that. So to access, we need to sort of complete the API here. So we have some, again, some usual suspects here. Well, we have valid, did I get ham here? We have get with the const version and everything. And the nice thing with get is if I call get and, there wasn't a T there, I'm going to rethrow the exception that was there. So actually, the get functions here are what allow me to use the expected thing as if it were an actual T, not an expected, because I just write parse int dot get, and then everything is going to go the exceptional way with throwing exceptions and all that. Or I could actually look for test valid and make decisions, right? And the most interesting function probably, which I alluded to a bit in the past, is, well, a query. So this is, again, a member function of expected. And the query it answers is, do I have an exception of type E? Is there, in the guts of that expected, is there an exception of type T, of type E? And the implementation is equally interesting because what it does is it actually rethrows the exception that was there, and it catches either E, a const E reference, or nothing. And only in the case, actually, there was An either is going to return true. In all other cases, it's going to return false. Yes? What can't I use type ID here? Excellent question. Let me take another question to combine them. Yes? That seems extremely slow. It is extremely slow. So I'm going to prefer, I should add a comment there. This is extremely slow. So to answer the other question, why can't I use type ID there? Because of the way exception PTR is designed. The way exception PTR is designed is it encapsulates an exception, but you don't have access to its type. You can only rethrow it, copy it around or whatnot, and rethrow it, but you can't actually get access to its type. Scott? It should be, so Scott pointed out that even though it's called exception pointer and it has the copy semantics of a shared pointer, if you wish, it actually doesn't have dereference this pointer, so you get back the exception. It's untyped. So it's not exception PTR of T. It's an exception PTR that's completely opaque. It's like, it's like a handle, right? So we can't use type ID here because there's no, there's no query available for exception PTR. So this is, yes, extremely slow way to probe if a particular expected contains an exception type of a particular base. Yes? The question was, well, since you have functions that can still throw, doesn't part of your argument get diluted because you mentioned all of these things that you want to do the non-exceptional way? Actually, this page is, I put it together with this purpose in mind because I have the valid here at the top, which is important. Because if I call valid and it returns true, get is going to guaranteedly not throw. Right? So the idiom in which I don't throw is if valid, get, and else I'm going to do the whatever exception case. So my point is here that I have the chance to get without throwing. Because I call valid. I can guard my code by calling valid. And that's valid actually enables this style of error code checking. The compiler doesn't know that. That is correct. What the compiler will know is actually it can actually get rid of this code, the inliner. So because after inlining you get like got ham, and got ham is known to be true, and actually the compiler is going to actually it's going to eliminate this code. So this is an easy target because these two functions are obvious candidates for inlining. And since they are like together, you get rid of this. And since you get rid of this, actually the compiler may actually think a little bit ahead and figure there's no throwing going on in some cases. But there's no guarantee here, so your point still stands. At least in theory, there's no way to inform the compiler some code is never going to throw. Informally, you can get that guarantee. All right. Okay, well, icing on the cake. From code. Okay, so let's see what this guy is supposed to do. So we have f, which is actually a lambda. And then I say, well, I'm going to give you an expected, this is again a member function, it's a static member function, and I'm getting, from some code, I'm getting expected, which goes like this. Well, either I'm going to return expected initialized with fun, or if that code throws, I'm going to return from exception of the current exception. And the nice thing is, you actually get to say, auto R equals expected of string from code, and you put any code here that returns a string, and you just collect the string. Make sense? So again, what I want to do is initialize with some lambda, some lazy evaluation if you wish. And what this initialize is going to do is it's going to execute this code and initialize the result appropriately, either with a legit string or the exception that produced the string. Again, this is icing on the cake. It's nice to have. It's nice to have, like, I'm just initializing from some code instead of actually executing some code and then initializing the thing. Makes sense? Question about, yes? Is there any way to inform the compiler that f must be a lambda? No, but I can tell you there's a way for the compiler to inform you it wasn't. Right? All right, so let me qualify that. You could with there's a round of There is not a reliable way, because I don't think C++11 contains any way to say, does f represent something callable? Is it, Herb?
Probably tell if it's callable, but there's no way to tell it's a lambda. Certain kinds of lambdas do happen to have a particular type, but that's only if they don't capture anything, and only certain lambdas. It's just another function object. Usually I would ask, why would you want to know?
Maybe you'd want to know because you have overloading and such going on. I mean, the general case, and you want to prevent other cases in the in the expected code. You want them in the client, like the classic reasons.
So then you don't really care if it's a lambda. You care if it's callable.
Right.
Then any function object. I mean, the lambda just turns into a function object.
Right.
That's why you
Is
can't
there a way
distinguish.
to say if f is callable?
If we had concepts, Bjarne would say we should have concepts for callable.
Or if you had, constrained templates.
But I believe you can do it with enable if and a callable meta function, but I'd have to try it to be sure.
Right. So enable if would be the obvious route. The question is whether I have something to pass to enable if that's a Boolean, if the thing is callable or not. So there's a question here. Yeah, yeah, exactly. So we're looking at can I actually execute? Can I evaluate fun with parentheses like this? Right. It's callable with no arguments if you wish. So I don't know of any reliable way. I could tell in other languages that shall not be named, but not in this one. All right. So yes, can we detect using decal type? Yeah, but decal type, you got to pass some valid code to it. Otherwise, it's gonna stop compilation. So essentially, what you're saying is that you're passing this to decal type, and you see if it's a string, right? So decal type of fun paren, it's string. So the question is, can I actually define is callable using decal type in its definition? You can't, because if decal type is passed an invalid expression, it's going to fail to compile. So there's no way in C++ to say, may I compile this code, and is it going to return the type string or not? So because of that, there's no way. So you need some compiler support for that intrinsically. Questions? Yes? Why don't you use an std function? Because that would be much slower than otherwise. So it's nice to have a template there because the template is going to be in line and everything, whereas std function is going to, in many cases, need to use an indirection and dynamic allocation. All right. Okay. So much about icing on the cake, and so much about this working. Okay. Okay. And let me show you an example of how this whole thing is used, because we talked about implementation so much. So let's see, I have a parse int, and it takes a string and returns an expected int, and I have a result. And if I detect a non-digit, then I'm going to return expected int from exception, and I'm going to pass whatever exception I want by value, like the doctor prescribed. And if I have too many digits, then I'm going to return expected int from exception out of range. And ultimately, I'm going to return result, which is going to be implicitly converted to an expected int, and it's all going to work. Now, this is the slide that got Herb incensed. Wow, Herb incensed. This is a slide that incensed Herb, all right? Pun not intended. So, because he said, whoa, the usage looks awful. This looks nice. This is good. This one line is good. This is bad, and this is awful, right? So what he wanted to propose in our rare phone conversation was, how about this? How about we make a simple simplification. How about we say you never throw anything that's not inheriting std exception? Wow, that's interesting, because you don't get to throw an int. So all of these edge cases go away, right? Do you throw anything but std exception derived? Okay, do you throw std exception derived? All right, so good. So hands are up. That's encouraging. So you may actually use your own hierarchy, but in any case, you're not throwing things like, int or, primitive types and stuff like that. So in that case, you can actually design things with enable if and such, which Herb is going to explain tomorrow, that actually allow you to say return std invalid argument and return out of range. which is very nice. You just return, and the compiler detects whether it was an exception or it was ham, right? Very nice. And again, let me underline, I agree with that design. It wasn't what I came up with naturally. Yeah, so if you get into these weird cases when you expect an exception, then not good. Then it's that essentially expected of exception is not going to work anymore. You can't actually have it. All right, so on the caller side, well, I'm reading a line and I'm parsing an int, and I could call .get immediately. In which case, it's just classic exception handling scenario, right? It's absolute classic exception handling if I just call .get. Otherwise, I may parse an int and then say, well, am I valid? In which case, maybe I can see, oh, well, was it an invalid argument and such? Then I'm going to handle it, and then I'm going to get. So we have both idioms available with this abstraction. So we have the .get idiom, which is exceptions all the way. Or I can get to manually test valid and look at things and do whatnot. All right. In the aftermath of stood exception, we have an encoding of a value or whatever happened in attempting to produce that value. We group data with error flow, and I think that's very nice, very remarkable. It's non-serial in nature. You can have an array or a vector or a list or a map of exception of expected and whatnot. There's no problem there. It supports two different types of coding, the classic error handling and you can actually have arbitrarily rich error codes, which is a net gain. We're going to, with this wrap up expected, if you have any questions, yes. Right, actually somebody pointed that to me too, which was, well, even if I don't use exceptions, expected is good because it groups the code with the value with the error, and you can actually abort if you call without valid, right? If you call get without valid, you can actually abort the program or whatnot. And still, it's a nice encapsulation of the value and the reason that, the reason that was there that prevented creating that value. Yes, Tommy? Aren't you Tommy? Sorry. Richard, sorry. So I'm not sure I understand the question. So you have like the pass-through scenarios in which you get an expected and pass it along, right? Right, so the argument is, well, this has a native disadvantage of classic error handling with error codes, which is I'm going to, if I don't check for .valid, I can actually go all the way through the thing like a hot knife through butter and have errors undetected, right? I agree. Here's a possible change to the design that could actually enforce that. So let me get back to, that's a very good point. So let me get back to valid here. So you can actually, if you want to enforce that every exception is looked at, what you could do is you can have a second Boolean, which is 8 ham. Okay? So you have got ham and you have 8 ham. So if somebody calls valid, you set 8 ham to true. Initially, it's false. So initially, it means nobody looked at it. And upon the first call to valid, you're going to set 8 ham to true. In the destructor, did this guy eat his vegetables, okay? Did the code actually look at the validity? If they didn't, and if there's an exception in there, then, make some noise. Raise a point. How do you raise a point? That's another good question because you can't throw from a destructor easily. Well, do you have a logging in your application? You can log on there. You can say, there's some unchecked exceptions here that went unchecked. Actually, so we have, like at Facebook, everything logs everything. There's a lot of like petabytes of log files and stuff. So actually, for us, it's a very good solution. I'm not sure if it's appropriate for all cases. So, it's sort of an open question. But you could do that in certain circumstances, yes. Exception pointer is akin to a shared pointer in the sense that, but it can hold actually something else than stood exception. And the way it works, it's a type erased shared pointer. It's like shared pointer to void, because that's engineered to use type erasure to call the right destructors and whatnot. So, yes. It's not a good time. I think the destruction time is a bad time to make a lot of noise. But yeah, I'm just mentioning that as a possible design. If there's a better design, I don't see it right now. So I agree that it has these advantages. All right. So with this, we're wrapping up the expected abstraction, and we're going to move on to scope guard 11. I'm going to not describe the original scope guard. I'm going to sort of interpolate a bit. I'm going to insist on the new implementation. Again, I should mention, if you go to github.com/facebook/folly, you're going to see a very nice library, some of which I've worked on. And it does have an implementation of scope guard. All right, so the old scope guard was introduced in an article back in 2000, wow, 12 years ago. And actually, I still have people writing me email asking, you don't have a legal attribute, you don't have a copyright attribution in your code, can we use it? And actually, yeah, that's true. So I have like lawyers writing me email. So our developers want to use scope guard. And it doesn't even say it's in public domain. The reality is, in 2000, I was not very sophisticated with those matters. I'm not now even, but back then I was even worse. And I just put a code as you have the code. It doesn't say like, this code is in public domain. So I sort of, and then there's Joshua Lehr, who improved scope guard a bit, and I'm forwarding all of his emails, all of these emails to him, and it became a sort of a problem. So just so you know, I grant, it's in public domain, I grant every use of that code, which actually is not, finally it's obsolete now, so we get to use the properly public code. All right, so it makes transaction code linear. I'm going to explain in a minute what that means. It's lightweight RAI idiom, and it scales well to transactions containing many steps. So let's see. Very generally speaking, whenever we want to do some action, we might have some cleanup to do. May or may not, right? And after the action, we may want to execute something after the action. And if the next step didn't work, we may need to roll back whatever the action did. So we have four notions. First, we have a notion of action. Second, we have the notion that I always need, after I've done this, I need to do that. And then I'm going to have like the following steps of the, after the action. And in case the following steps fail, I'm going to need to do some rollback. This is a very generalized flow of work with general like composing actions. So, let's look how we typically implement them. Like in C-style code, we go like, let's assume action returns a Boolean. We go like, well, if action, then, if action succeeds, I'm going to always do the cleanup, and I'm going to do the rollback only if next failed. So far, so good? I'm sure this is a pattern that we semi-consciously wrote like, many times. So this would be a C-style sort of doing things. Then I have like, I'm calling this is no typo. C+. I've seen this term like, oh, you're using C+, which means C and classes and overloads. That's pretty much, and virtual, maybe a virtual here and there. And that's C+. In C+, the way we do this is, well, we define a nice class, and then we say, well, in the constructor, I'm going to do the action. In the destructor, I'm going to do the cleanup. And then I need to sort of do this awkward thing. Well, I'm going to try next action, and if it didn't work, I need to roll back and then rethrow. Again, this is a pattern that I'm sure many of us have written many times. So the problem here is when we start discussing composition. When we start discussing composition, it gets a whole lot more complicated, because composition means I have two of these, right? And I need to compose them. Well, and what I did was, I'm not even sure it's entirely correct, but what I did was this. I took this, and I replaced next with the whole expansion of the next action, right? So there we go. So if action 1 And if action 2, then if next 2, then rollback 2, rollback 1 in this order. So I need to roll back in the opposite order, destructor style. And then I need to clean up 2 because action 2 has succeeded. And then I need to, if action 1 succeeded but action 2 did not, I need to roll back 1 and clean up 1 and so on. So, you know, I'm not claiming this is something I should do. I'm just saying natural composition actually leads to this, right? With RAI, it's quite a bit different. So I have, again, like, you know, class number 1, class number 2, and we compose, and we need to have nested try statements. I hear a yawn there. I take it it's against this, not against the speaker. So, well, we have try, and so we first construct this guy. If this guy fails to construct, we're good, no problem. Then we try to construct the second guy. If that didn't work, I need to roll back 2, and I'm going to try next 2, and so on and so forth. Now, here's the thing. You don't always have these patterns because sometimes this guy is missing, in which case you don't need all that try statement, or this guy may be missing, in which case you don't need the other statement. So it's not always you need this. I'm just trying to figure out the general pattern that's out there. Okay? My general point here is that when you try to compose with either error codes or exceptions, things get very hairy very fast. Okay? So what I'm saying here is that whenever you try to compose, you're dislocating the normal path of execution, and you're nesting it inside another pattern. And in that case, you're going to have complications. Let me explain what I mean by dislocation and nesting. Let's go back to the first example here. My normal code is already embedded in a larger structure. It's not isolated. My next is even deeper. It's 2 levels embedded into a larger structure. These are normal path actions. They are dislocated from the top level and embedded in other structures. As soon as I take it out of the normal path, as soon as I take the normal path out of the top level and I'm embedding it somewhere else, it blows up when you're going to compose. Because composition means you're going to have to expand all of this stuff when already deeply nested. And it explodes into what we've seen, right? So the failure here is to recognize that the normal action code should not be dislocated from the top level. This is going to become a lot clearer when you're going to see where I'm going with this. So I hope you agree that if you want to compose with either error codes or exceptions, it's not going to go all that well. All right, so with scope guard, it works very nicely as follows. Action at top level, and I'm creating a scope guard that does the cleanup. And I'm going to have another scope guard that's the rollback. And then I'm going to do next, and if next succeeds, I'm going to dismiss the rollback. And if next throws, then this is not going to be dismissed, so the rollback is going to be in effect. There's no explicit flow here. And this does everything that the other 3 examples do, composed, right? Let me clarify. This is actually working code. So scope guard is a function, and it takes a lambda. Another function calls a lambda. So scope guard actually takes a lambda and promises me that it's going to call its code in the destructor. Unless I get to call dismiss, in which case that call is not going to occur anymore. Make sense? And the advantage of it all is that right now I have no more flow of control going on for the normal path. Yes? Wouldn't it make more sense to attach both lambdas to one object and call commit? Actually not, because the way it happens with C++ is if something throws, you don't reach some code. And let's see. I think you can find some examples in which committing, like you explicit commit would make more sense, but I think most of the time you want to actually roll back things. You want to undo things. This is more closer to usual C++ style. But I think you have a point that the alternate route in which you say, well, I'm going to say G2, and I'm not going to call this unless you commit, in which case it's going to happen. But the classic scenario that I've noticed again and again in code is people do actions, and then on the exceptional case, they actually want to undo them. So, but I think that would be a valid design too. All right. So this is actually working code. And what's nice about this? Composition. How about this? This is 2 levels composed. So I have action 1, and I'm planting the cleanup and the rollback for 1. Action 2, I'm planting the cleanup and the rollback for 2, and then I'm going to do whatever is after the second action. And then I'm going to do G2 dismiss and G4.dismiss. By the way, question, shouldn't I swap G4 with G2 here? Yes. The destructor will be calling in reverse order anyway, but my point is, shouldn't I dismiss the guards in the reverse order of their construction? Because the destructors, I agree, they're going to be called in reverse order, but shouldn't I also do the dismiss action in reverse order? There's a simple answer to that. Yes? No throw. There are no throw. The order doesn't matter. If they threw, it would matter. There are no throw. They just set a flag. They say, just don't call this function. So let's implement, yes? Yes, if rollback throws, you have an unsolvable problem on your hands. It's unsolvable. Rollback can't throw, because otherwise you can't. It's impossible. You can't put the torpedo back in the bay, right? You can't. I'm telling you, if rollback throws, it's an unsolvable problem. I'm not even trying to handle it. Yes. You don't get to the dismiss. So if next 2 throws, that's the scenario. If this guy throws, then I'm not going to go to the dismiss steps, in which case I need to roll back whatever these guys did that next depended upon, right? So there are a lot of scenarios, like I'm adding to a database that's online and to a replica and things like that. And if one fails, I want to actually undo the other 2, right? And that can't fail. Where are you? That can't fail, my friend, okay? Rollback can't fail. If it fails, all of these slides are worthless, okay? So, well, let me actually define a macro edition now, which is kind of interesting. What if I define a macro scope exit that actually has, the scope exit and the scope exit, and I have much fewer guards. And, sometimes I don't need any rollback, in which case I just have a very nice abstraction, which is a pseudo statement that says whenever the scope is exited, execute this code. It's deferred execution. Very interesting. Let's see how this is actually implemented. Painfully close, it would be nice to have another pseudo statement, scope fail. If the scope is exited via an exception, I want this to happen. Wow, that would be interesting. It's impossible in C++11. I've tried valiantly to do this at Facebook. I failed. I was like, GCC assembler, I would do anything. It was impossible. Just a sec. I need to take fewer questions because I have like only a few precious minutes left. So it's impossible, but Herb and I, want to talk about this on how to integrate this within the next TR to make this actually possible, because it's extremely useful. So how does it work? In C++98, we had a very elaborate implementation. If you Google for scope guard, you're going to see like 3 entries about telescopes, scope guard, guns, stuff like rifles with scopes, and there's a scope guard that protects the lens. And then there's going to be my article there, right, with Petru. So there's an elaborate implementation. In C++, you can exploit 3 key things: type inference and auto. Very nice. There's no need for type erasure. We can exploit lambda function because we can defer any code for execution. And move semantics, there's no spurious double cleanup, as I'm going to show in a minute. Let's see. Very simple. Scope guard, the function to be executed, and whether it's active or not. I initialized, by default, it's going to be active. And that if you do the transaction thing, you would put it to false and you have a commit, right? But by default, we're going to be active. And the destructor, this is the interesting part. If active, do it. And then dismiss, I'm just setting active to false. As the gentleman mentioned, it's just a no-throw function that sets a flag. There's no danger in using it anyway. To be continued here, let's continue the scope of scope guard. And I've just added some, for readability, I've added some things here. Like, we're not using the default constructor. It doesn't make sense to have a scope guard that's default constructed. We're going to refuse copy, but we're going to allow move copy, because we want to have the function scope guard that actually initializes the scope guard. So we refuse value semantics, but we have move semantics. And of course, we want to dismiss the original because we don't want to clean up twice, right? So when you move copy, you put the lambda, you copy the lambda and stuff, and you say the original, and say, oh no, don't call, I'll call, right? And finally, the classic trick, we have a template class and we want to associate it with a template function because the template function can use type deduction, which the class can't. So we have this scope guard function with a lowercase s that takes any lambda and is going to return me the appropriate type, and it's going to do the moveroo and all that good stuff. Awesome. That's it. This is it. And actually, the most interesting part is, before the most interesting part, here's the simple use. So I have a name, delete me, and we have mks temp, make a temporary name with, replace those x's with stuff. Oh, wow, all that good stuff, And then we have a scope guard, and in the scope guard, we're going to close the file and delete it. So this is my cleanup action. Whenever I exit the scope via any means, I want to close the file, clean up after myself, right? Clean everything. And then I'm going to allocate a buffer. I'm going to free it later. And then I'm going to use FDM buff. I can do anything here, returns, throws, whatever, early returns, you name it. The point is the buffer is going to be automatically deallocated and the file is going to be closed and deleted. Awesome. And the most interesting part of this all is the macro. All right. Where should I start? Well, I should start with this. Anonymous variable. So, if you want to define scope exit, what you want is to actually introduce an anonymous variable. You want to introduce a variable that has a name that's impossible to clash with anything else. So I'm going to say, well, the anonymous variable of scope exit state. And let's see the definition of that guy. Did you ever see this? These two. Hands up if you've seen. Oh, all right. No need for explanation the -1 minutes I have. So this is how you concatenate symbols in C++ and C and C++ for that matter. It's just due to the way the tokenizer works, which is as slow as it could ever be. Tokenizer in C and C++ is very slow. So we concatenate via an indirection here, and then we have this magic counter thing, which MSVC and GCC implement, which is a counter that gets incremented with every use. So very interesting. So then we say, well, I'm going to concatenate the string with counter. Otherwise, if I don't have a counter, let me concatenate with line. So what I'm getting here is anonymous variable of this guy and 434. And then 435, and so on. So for every counter, I'm going to get a different anonymous variable. Very nice. So I'm creating an anonymous variable. So this is my scope exit pseudo statement. So I'm creating an anonymous variable with this name, right? That gets initialized with detail scope guard on exit plus an unfinished lambda. Because in the detail namespace, I go and say, well, let me plant an operator plus that takes this enumerated value of which use is null. I'm not using it. I'm just using it for the sake of its type. So I'm going to say this guy Okay, so I hope that was a sort of an admirative laughter. Okay, this is like, ha ha ha, that was good. All right, so I define operator plus between the enum I don't care about much except for its type and the lambda. And then I have the enumerated value of which I don't care about, plus the unfinished lambda, and then the user comes with a curly brace and writes the code. And when you expand the macro scope exit, open curly, F close, right? Close curly, right? So when they write that, they're going to get this, and plus the lambda, and then semicolon. They have to put semicolon after that pseudo statement, which is like the only drawback I see here, except for the very complicated implementation. And in the operator plus call, I'm going to essentially create the scope guard. And that's how it works. It's kind of funny. This is one of the interesting parts of this implementation because the C++11 makes the rest very simple. All right. So I'm going to sort of end here with the summary of this talk. So which one did you like best? Like expected more than scope guard? Who liked expected more? Who liked scope guard more? Half and half. All right. To summarize, with these two abstractions, I'm not saying it's everything. I'm saying you get to make much more systematic error handling. Expected of T, apologies for the typo here, encapsulate values with their history of failure, and scope guard 11 encapsulates scoped control flow. With this, I'm going to be done, and I'll be here, of course, for further discussions if you want. Thank you.